This is the last configuration that we are going to look at. This is the common collector amplifier. Now, the input is taken at the base terminal and the output is at the emitter terminal. The collector terminal is to be at signal ground. That is why the collector resistance RC is eliminated. Signal ground means that at all frequencies of interest, the collector terminal must be grounded. And so, since the collector terminal is common between the base and the emitter by virtue of it being grounded, that is why we call it the common collector amplifier. Now, before we go into our usual analysis, let me point out a very interesting fact about this amplifier. Now, before we go into our usual analysis, let me make an interesting remark about this amplifier. Unlike the ones that we have seen before, this one is non-unilateral. What this means is that the input resistance depends upon the load and the output resistance depends upon R sig. So, let's draw the small signal equivalent circuit model. Here we are, and we have included R0 in our model. Why? Because test results show that R0 cannot be excluded here without making significant changes to the results. Luckily for us, R0 is in parallel with RL. They have two terminals in common, ground and the emitter. We have used the T model again. Why? Because the resistance RL parallel with R0 is in series with RE. Therefore, our analysis is quite simplified. We can simplify our analysis even further by employing the resistance deflection rule. Let me show you how. Here we go. Now, notice that while we have multiplied the resistances in the emitter, RE, RL and R0 by beta plus 1, we have severed connections with the collector terminal, namely the current source alpha IE. This is because we have translated our relationship between IB and IE directly into our resistances. This works because the voltages remain the same. So let me completely remove the collector terminal, and now we can carry out our analysis more easily. R0 also has been brought down to show how clearly it is in parallel with RL. Now we write an equation for Rn. Rn equals Rb parallel with brackets open beta plus 1 brackets close brackets open Re plus R0 parallel with RL brackets close. Easy, isn't it? Employing the same rule, we can find the overall voltage gain. But to make our analysis simpler, we can employ the Thevenin theorem to the input side of the circuit. Here we are, and now it is very easy. All we have to do is find V sig in terms of VB and VB in terms of V0. So, this can be jumbled up together in one big voltage divider equation. Let me write it down. Here we go. And we observe that the voltage gain is less than unity. The denominator is clearly larger than the numerator. However, if we impose the condition RB is much larger than R sig and beta plus 1 RE plus R0 parallel with RL is much larger than R sig parallel with RB, then GV is very close to unity. Thus, the voltage at the emitter, that is V0, follows very closely the voltage at the input. It gives the circuit its name, emitter follower. We can write an equation for R out. Here we are. And now notice that Rn and R out clearly indicate that this amplifier is non-unilateral. Rin contains RL and R out contains R sig. Now, since the input resistance of the common collector is so high, it finds application as a voltage buffer when we connect a high resistance source to a low resistance load, all the while keeping the voltage gain almost constant. Why did we say that the output resistance is low? Remember that R0 is usually much larger than the parallel component between the brackets, that is RE multiplied by beta plus 1 plus R sig parallel with RB. So R0 can usually be neglected. RB is usually much higher than R sig. Therefore, you are left with R sig and RE, both quite small. The resistance reflection rule may sometimes seem like much of a hassle, but in reality, with practice, you can mentally do the calculations and reduce your time considerably. As a task, try the resistance reflection rule on the output side. That is, instead of multiplying beta plus 1 on the emitter resistances, multiply the input resistances with beta plus 1. This way, we will be reflecting resistances to the emitter side. You should have identical results for Rn, Gv and Rout. Also note that we have not calculated AV here. Why? Because Gv is much more important. Its unity value, or I should say almost unity value, gives the amplifier the name emitter follower.